Also on Monday, quiz number 1 will come online. Quiz number 1 will cover the same chapters, so that's 12 through 16. I believe it's worth 20 points. Please practice it. On the exam, there will be multiple choice questions, and many of the questions on the quiz will be multiple choice, so it's nice practice. Any question before we get started? Yeah.
Yeah, so the chemical is going to be the 29th.
Sorry?
The
Quiz will, yeah, I think so.
So,
And the exam is later.
You just said next Monday.
Whatever's a week later.
so that quiz will be only available that day online. Is that correct?
Probably I'll leave it up for more than just one day.
And one attempt per question?
Yeah. All right, electrophilic aromatic substitution. Back when we introduced the concept of benzene, we started off by saying that benzene was a real anomaly because it didn't do things that other alkenes did. It was, well, the tetravalent structure was accepted pretty much, but there were problems with it, and the problems were something like this. If you took a simple alkene with bromine, the reaction is very, very rapid to give the trans 1,2-dibromide. In order to get a bromine onto benzene, you had to use bromine, but in the presence of a Lewis acid. Here we're using iron 3 bromide. And we only add one of the bromines to the ring. The second one shows up as HBr. These are obviously different mechanisms. Just remembering what we said about benzene, remember that it really is not cyclohexatriene. We will draw it that way, and we will use the cyclohexatriene a lot, because it's going to be very useful in describing resonance structures involving the ring. Really, it's this assortment of 6 pi clouds, or 6 p orbitals, forming a cloud above and below, and we've seen this many times. The electrostatic potential map looks something like this. Because of that, and in honor of this beautiful thing, quite often benzene is drawn this way. Remember, they're both acceptable. Any questions? Well, let's start off with our beautiful electrostatic potential map for benzene. Now, this is called electrophilic aromatic substitution. Aromatic, of course, refers to the benzene ring. An electrophile, simply it means something that seeks electrons. Typically, it's a positive species, and it's something that is looking for electrons. So if you were an electrophile and you saw a benzene ring sitting there, quite obviously the place where you would find your electrons is going to be right here in the middle of the pi cloud. The first step in electrophilic aromatic substitution is actually left out in most textbooks, but it's a very simple pre-equilibrium. The electrophile simply comes and sits down in the middle of this wonderful pile of electrons. Now, this is a very rapid equilibrium process. Goes on, goes off, goes on, goes off. Nothing happens until this pi complex rearranges to form what's called a sigma complex. So what has happened is this electrophile is sitting there. One of the, or some of the electrons, 2 of the electrons from the pi system then bond here, and we actually form a covalent bond now between one of the ring carbons and the electrophile. Now, because we've taken electrons from the ring to do this, this leaves this ring positive. So our first intermediate here, the sigma complex, is a cation. Now, this happens because this cation is in this ring, and it's a conjugated system, isn't it? Think back to chapter 12. If we take this and we move this electron pair up, we can shift this positive charge from here down to this carbon. Likewise, we can draw another resonance form. We can take this pair of electrons, move them in, and draw a third resonance form. So the positive charge from our sigma complex is delocalized over these three carbon atoms. All right, because of that, the sigma complex does have a fair stability. In order to get products, the product is going to wind up as the electrophile bonded to an aromatic ring. So in order to do that, we have to grab this extra proton, rip it off, move the electrons back into the ring, and then we can do something like this. Any base will do it. Any base will work. We simply pull the proton off, the electrons move in to form a double bond, and we're back to an aromatic system. We have lost H, Br, or H whatever. So we've lost the hydrogen from the ring, and our electrophile is now covalently bonded. This is the total mechanism for electrophilic aromatic substitution. Any question on the concept here? Yeah.
So that's for any of them?
For all the electrophiles, they're going to follow the same basic mechanism. Pi complex to sigma complex. Sigma complex is resonance stabilized, lose a proton, and get the product. So all we need to do now is to look at the electrophiles. There's just a handful that we're going to deal with. The first one we started with was bromine in the presence of the Lewis acid, iron 3 bromide. Remember, Lewis acid is an electron acceptor. What happens is the iron atom here will accept a pair of electrons from the bromine of Br2, and we will form a species very similar to Br+. With something like bromine, it probably really is Br+. A nice, stable. Remember, bromine is such a big, polarizable atom that you can form a nice, stable bromonium intermediate. But it starts off again with Br2, simply chelating to the iron. We wind up with Br+ as our electrophile. We can also do this in what we will call the FRIEDEL-CRAFTS reaction, using an alkyl halide. It's a very versatile reaction, does have its problems, but what it allows you to do is to take an alkyl group with a halogen on it, again in the presence of a Lewis acid. The bromine will chelate once again. The difference here is that because the methyl carbocation would be so very, very unstable, it probably doesn't really split off. The actual electrophile is going to be the whole thing here, but this is the center that's going to add. FRIEDEL-CRAFTS acylation. You can do the same sort of reaction with an acid halide. Now remember, an acid halide has an alkyl group or aryl group of some sort out here, carbonyl, and then a halogen. The same basic mechanism. halogen will coordinate with the iron 3 bromide. Now, when it does that, it's going to put a positive charge out here. Unlike the methyl carbocation, in this case, we would form an acylium ion, wouldn't we? And remember, acylium ions, oxocarbocations, or something like this, are very stable, relatively stable, as far as carbocations go. The lifetime of something like this is about 10 to the minus 9 seconds in water, but still that's relatively stable for a carbocation. We'll also look at simple nitration. In nitration, you take nitric sulfuric combination. We did that in lab, remember? The electrophile here basically comes from dehydrating nitric acid. We form NO2 plus, stable species, but this is the thing that is the actual electrophile. Finally, we're also going to do sulfonation, fuming sulfuric acid. Fuming sulfuric acid is sulfuric acid with SO3 dissolved in it. Very, very powerful stuff. What you do is simply protate the SO3, make HSO3 plus, and this is our electrophile. Any questions? So the basic reactions we're going to look at are going to be these. We're going to start off with benzene. In the presence of halonium ions. So we're going to simply attach the halogen to the ring to make an aryl halide. Nitration. Again, our electrophile here is NO2 plus, and we get the nitrobenzene in this case. Sulfonation. HSO3 plus is our electrophile, and we form the benzene sulfonic acid. Now this is an organic equivalent of sulfuric acid, so it's a strong acid. But instead of having another proton out here and hydrogen, it's got the aryl ring. Alkylation. Like I said, this is going to be FRIEDEL-CRAFTS. The neat thing here is you can take a wide variety of alkyl groups and very simply attach them to the benzene ring. And then finally, acylation. Here our electrophile is the oxonium ion here, adds to the carbon, and we wind up with an aryl ketone. In terms of electrophilic aromatic substitution, these are the 5 reactions we're going to deal with. Any questions? All right, let's look at these one at a time here. If we take benzene in the presence of iron 3 bromide and bromine, we can also do this with aluminum bromide. That's also a very good Lewis acid. But bromine, so either one of these works. Our electrophile. I'm going to draw the electrophile like this as shorthand, because I use dashes here to show that this is a resonance hybrid, and that we have a positive charge over the ring here. We will lose the hydrogen here. That will give us HBr as our second product, and the aryl bromide, benzene bromide, as our product here. We can do the same thing with chlorine. Chlorine with iron 3 chloride or aluminum chloride, either one. Same sort of electrophilic addition intermediate here. Again, we lose the hydrogen and we make chlorobenzene. We can't do it with fluorine, but we can get an iodine on the ring. It's a little trickier. We have to do something like this. use iodine in the presence of copper 2 chloride. So that's the only Lewis acid that works here. But again, you form the same addition intermediate, and you wind up with the aryl iodide. Any questions? When we nitrate, remember our electrophile is NO2+. So this will add through the nitrogen. We will form this intermediate sigma complex. Remember, these are all positively charged. This will then lose a hydrogen, and we will form the aryl nitro compound. Sulfonation. Once again, we take SO3 in the presence of sulfuric acid. We protonate it to get the HSO3+. That's the thing it adds. Remember, it adds through the sulfur. We lose a proton here, and we get the sulfonic acid. Make sure you understand the nomenclature here is a simple sulfonic acid. The FRIEDEL-CRAFTS alkylation. This is a really neat reaction. Again, we're just going to do it here with a methyl group. We'll see you can do it with lots and lots of different things. Our electrophile is probably a complex like this. It's going to add through the methyl end, and we're going to form this as our sigma complex. Once again, we will simply lose a proton from our sigma complex, and we wind up with the alkyl benzene. The FRIEDEL-CRAFTS reaction was actually discovered by Friedel and Crafts. They were German chemists. I did some work on this, actually as an undergraduate. Their write-up on the original experiment was fairly interesting. They were using benzyl bromide as their alkyl bromide here. Remember, the benzyl carbocation is very stable, so this reaction just really worked well. And apparently, or at least the way they wrote it up, they had some students or some tech or somebody trying lots and lots of different things, took benzene plus benzyl bromide, and finally added aluminum chloride to it, just to see if it could make something happen. And it did. In fact, it reacted so violently that everything came squirting out of the flask. They didn't have hoods in those days, so it went straight up to the ceiling. And they literally isolated the product from the ceiling. Very first FRIEDEL-CRAFTS reaction. Now, as neat as the FRIEDEL-CRAFTS is, it does have problems. We can only use alkyl halides. So an aryl halide or a vinyl halide does not work. It's got to be an alkyl group in between the ring or the vinyl group. If we have electron withdrawing substituents on the ring, the reaction just plain doesn't work. Now think about this. Electrophilic aromatic substitution. The electrophile is coming in looking for electrons, isn't it? If it's looking for electrons, and you have one of these groups on the ring that's sucking the electrons out of the pi system, it doesn't work. So in general, we'll see that all of these electron withdrawing substituents severely deactivate or slow down this process. With FRIEDEL-CRAFTS, it just plain doesn't work. Once you get one alkyl group on, quite often you'll get a second and maybe even a third. So multiple substitutions often occur. You've got to be real careful with your conditions to only get one. And finally, the real killer here. Because the electrophile has carbocation character, we can get rearrangements. This is a standard carbocation rearrangement. Remember, we talk about alkyl shifts, we talk about hydride transfers, etc. We just rearrange the carbon skeleton so that we form the most stable carbocation. Let me show you why this is a problem. What if the entirety of the first hour exam was to suggest the synthesis of propylbenzene starting with benzene? Now, as of right now, the only way you know to do this is with a FRIEDEL-CRAFTS alkylation, right? So, okay, you say I can do this. What I'm going to do is take benzene and something like propyl chloride. Dump in a Lewis acid. We'll call it aluminum chloride. You're hoping, beyond hope, that you will simply form the propyl carbocation, and that will add to the ring. Unfortunately, this is a primary carbocation next to a secondary center. Remember, secondary carbocations are much more stable, so this will undergo a hydride transfer. Hydrogen with its electrons just slides over from here to here, and we're left with the 2-propyl carbocation. This is the thing that's going to add to the ring, and we wind up with isopropyl benzene, not propylbenzene. So this is what we mean when we say the FRIEDEL-CRAFTS reaction does not work if your alkyl group is prone to carbocation rearrangements. That's a bottom line. Any alkyl halide that can undergo a carbocation rearrangement will not work in a FRIEDEL-CRAFTS alkylation. Now later in the class we'll see there's a cute way that we can use to get around this problem. But that's coming up. Any questions? The last one we want to talk about is the FRIEDEL-CRAFTS acylation. This is a very nice little reaction. We're going to use an acid halide. So the acid halide can either be an acid bromide or an acid chloride. Again, you need a Lewis acid of some sort, iron 3 bromide or aluminum bromide. That would work fine. What we're going to do is form an acylium ion like this. This is going to add through the carbon, right here, through this carbon. We're going to lose our hydrogen, and we wind up with the aryl ketone. Unlike the FRIEDEL-CRAFTS alkylation, the acylation really is a sweet reaction. We do not get multiple substitutions. That is, we only put one on the ring. We do not get a carbocation rearrangement. Now, why is that? Well, because the oxocarbonium ion you're starting with is very stable. So it's not going to undergo rearrangement. Again, if you have electron withdrawing substituents, it's not going to work. And if you don't like using an acid halide, you can also use a simple acid anhydride. Same thing happens here. We're going to split this off. In this case, we would form acetate anion and the acylium ion. So anhydrides or acid halides. Any questions? All right, we've only got 5 reactions here to worry with. That's good news because we have an exam coming up, right? Let's just look at some very quick ones here. Take your sheet, run through these, and jot down the products. For our first one, we see we have chlorine in the presence of iron 3 chloride. Iron 3 chloride is our Lewis acid. We remember this is going to form a simple sigma complex with the chlorine attached that will lose a proton, and we will form chlorobenzene as our product. Our next one, we're taking fuming sulfuric acid. That is sulfuric acid with SO3 dissolved in it. This protonates the SO3, that's our electrophile. The addition is going to be through the sulfur, and we form benzene sulfonic acid. Our last one, we're doing a FRIEDEL-CRAFTS acylation. Here we're using an acid anhydride instead of an acid chloride. Remember, what we do is split at the oxygen. So the acylium ion is going to be the other half here, and that's going to be this 3-carbon chunk. That's going to add through the carbon here, and we will form the aryl ketone. Any questions?
Can you show that last one again?
The last one?
The logic?
The logic. Okay, this is an anhydride.
Okay.
Okay? That's an activated acyl group. So it's an anhydride. What you do here is we're going to split on either side of the oxygen, either side. When we do, the electrophile is going to be the carbonyl and whatever else is attached. So in this case, we have the carbonyl and 2 more carbons, an ethyl group. This is lost as the carboxylic acid. This is the electrophile. This simply bonds through the carbonyl, and we have our 2-carbon chunk here.
Thank you.
Okay. All right, well, let's look at a couple multiple choice questions. Remember, we're going to have those on the quiz, and they will be on the exam as well. So let's just see what something might look like. This is not as trivial as it seems. Take a moment and read through it. We're going to make isopropylbenzene here. Isopropylbenzene is also called methylethylbenzene. And the question is, which of these sets of reaction conditions are going to work? Our first one here, we're dealing with 2-bromopropane. So that's our propyl group here with the bromine in the middle. Obviously, that's going to give the isopropyl carbocation, and that's going to work, isn't it? So A is good. Let's skip B for a second. We've already done C in the slide we looked at earlier. We took 1-chloropropane in the presence of a Lewis acid. That formed the 1-propyl carbocation, but that just rearranged, didn't it, to give the 2-propyl. So this guy is going to form, rearrange, and give isopropyl benzene as product. So C works. How about B? This goes all the way back to organic 1, doesn't it? Just quickly jot out the structure of 1-bromo-2-methylpropane. Hopefully you realize this has too many carbons, doesn't it? These guys have 3 carbons, this one has 4. That's going to be the long product. Therefore, A and C are the only things that work. Once again, C works because the primary carbocation rearranges. This is what this compound looks like. Again, it has 1, 2, 3, 4 carbons. Wrong stuff.
I thought the bromine and the methyl were next to each other.
1 bromo, that's 1 bromo, 2 methyl. Think 234.
I'm lucky to survive that one, to be honest.
All right, the next one. Here we're doing a simple FRIEDEL-CRAFTS alkylation. The question is, what is the electrophile in this reaction? Well, the electrophile is something that's looking for electrons, right? Chloride is certainly not looking for electrons. Benzene has them. This is the Lewis acid, isn't it? So by default, it's got to be this guy. But let's think about it. What we're going to do is chelate the chlorine to the aluminum. That's going to leave a carbocation, a carbon with 3 methyls, looking like this. Any questions? All right, well, you know what? If we only did electrophilic aromatic substitution on benzene, it would be really simple, and it would just be boring as all get out, right? We can also do this on substituted benzenes. With substituted benzenes, we will find that the substituent, this is R, whatever R is, will affect the reactivity of the ring. And it will also control where on the ring the electrophile adds. So that's where we're going. Going to affect the reactivity and where it adds. That's called the regiochemistry or the orientation on the ring. We'll talk about these in terms of ortho, para, and meta. Remember, this is para, that is opposite the group here. Ortho would be right next to it, either of these positions. And meta is down here in the 3 position relative to R. All right, we kind of have a feeling for this already. Because we said the FRIEDEL-CRAFTS reaction didn't work if you had electron withdrawing substituents. Now this is electrophilic, isn't it? So the more electrons you have in your pi system, the better off you are. Let's just look at some examples here. Start off with aniline. Aniline is aminobenzene. So this is NH2 attached to our benzene ring. Remember, the nitrogen has a lone pair of electrons. By resonance, it can move those into the ring. And when it does that, it dumps lots of electrons in there. Benzene, of course, is just by itself. Benzonitrile. The carbon-nitrogen triple bond is very electron withdrawing. So it does the opposite. It will suck electrons out of the ring towards itself. Start with benzene. We know what it looks like. Nice, big, happy pi system in the middle. If we put something here that's going to pump electrons in, we wind up with an electrostatic potential map, and you can see bigger electron cloud. These are the electrons from the nitrogen. Again, they're being pumped into our ring. With benzonitrile, we're going to suck the electrons out of the ring, and the thing is going to look like this. So if we simply did reactivity, if you were an electrophile looking for something to react with, this is better, this is okay, and this is bad. Very simple. More electrons are off, the better the reaction will be. When I say better, I mean faster. We refer to this as activating. These substituents activate the ring towards substitution. Down here we have deactivating. These substituents at the bottom here will suck electrons out, and they will slow the reaction down. All right, let's go back to that one.
I have a question on that.
Yeah.
So does that mean that all of the halogens will suck it out?
Halogens are very interesting. Halogens themselves are more electronegative than carbon, aren't they? So they will remove electron density. They'll remove electron density because they are more electronegative. But remember, they also have unshared pairs all the way around. So they activate the ring by resonance. So these are actually activating even though inductively they remove electrons. So they are less reactive than benzene, but they are not considered deactivating. They are still activating because of the resonance. All right, let's look at a nice, strong, activating substituent here. I'm going to use the methoxy group. This is anisole, it's called. It's methoxybenzene. Remember, the oxygen has two unshared pairs of electrons. Now, these are adjacent to the ring, aren't they? So that means we could take these, we can move them in, and put a negative charge on our ring. So we can draw a resonance form like this. Move them in, put the electrons out on a carbon, and wind up with a positive oxygen and a negative carbon. Now once we do that, we can do it again. We can take this pair, move it in to make a double bond. But in order to do that, we have to take this pair and localize it here. And finally, we can do this again. Move the electron pair in, localize these on this carbon, and get this as our resonance form. So our prediction here is that for anisole, we would expect a partial positive charge on the oxygen, and we would expect enhanced electron density here, here, and here. The resonance hybrid would look like this. Partial positive on the oxygen, partial negative, these guys, and this one. Now you see, this is why drawing the calculate form can be useful, because you can draw these resonance forms and make predictions. Everyone see how we did this? Make sure that you know how. Refresh in your mind how to draw resonance forms for an intermediate like this. Yeah.
I guess how does the resonance form help us, I guess,
Well,
in
the resonance form here predicts that we would get enhanced electron density here, here, and here, and a positive charge there. So this explains to us, if you will, why this ring should have more electron density, why it's activated, and why it should work better.
Okay. I have a question as
Okay.
well. So reviewing this, what chapter would I go back into? Because parts of it I see from the lessons from, what chapter should I touch on?
What, I'm
I can
sorry?
see the whole picture here. I'm not seeing the whole picture.
All right, one more time. We can go all the way back here and do our resonance forms again. Remember, in resonance forms, we're going to move electrons between either atoms with unshared electrons and adjacent pi systems. We're going to do this 2 electrons at a time. Step 1, let's move this pair in to make a double bond. That would give us 5 bonds on this carbon. That doesn't work, does it? So in order to accommodate that, we have to put these electrons somewhere. So let's just take and just put them on this carbon. If we do that, this is now a carbanion. We have 3 bonds to our oxygen, therefore it's positive. That pair of electrons shouldn't be there. I apologize for that one.
Yeah.
Ignore them. All right, now if we take this pair, move it in, localize the carbanion down here, do it again, move them up, localize it. We have negative character here, here, and here. Now we show this in the resonance hybrid as a series of partial positive and negative charges. This is our resonance hybrid. Partial negatives here, partial positive there. All right, so now we know 2 things. We know, we can understand, we can rationalize why the methoxy group is activating, because it's pumping electrons into the ring, right? Pumping them in. This also is interesting. These negative charges are located where? They are ortho and para to the methoxy group, aren't they? Now, turns out that if you do electrophilic aromatic substitution on methoxybenzene, the substituent will go ortho or para. So that's convenient. We can rationalize not just the reactivity, but the placement. Now, to dash your hopes and dreams, let's take this and actually look at the electrostatic potential map. we would expect, based on the resonance argument, that we would see enhanced electron density here, here, and here. Correct? That's what we'd expect. That's our prediction. If you calculate it, however, it looks like this. Now, if you look at the ring here, you can see our 6 carbons, but there really isn't a whole lot of excess electron density where you might expect it. Now that's disturbing, because we made a prediction and it doesn't seem to be that way. Let's look at nitrobenzene. Nitrobenzene removes electrons from the ring. Very electron withdrawing. So it's going to suck electrons up. We would expect a ring to have less electrons, and we can now compare it to what we have here. If you look at nitrobenzene, frankly, it doesn't look any different to me. So is this whole thing wrong? No, of course it's not. No, of course it's not. It just means it's a little more sophisticated than the simple explanation we gave the first time. Okay? If we want electrophilic aromatic substitution to occur, what's the one thing we want to form and stabilize? Not so much our product, not so much our reactant, but the addition intermediate. Remember, when we do our electrophilic substitution, we're going to form this resonance stabilized intermediate. The more stable this intermediate is, the more of them that are going to form, and the more product you're going to get. So the faster the reaction will be. If this is a really unstable intermediate, not going to work. If it's stable, you're going to get product. So let's go and let's look at the electrostatic potential map for something like this. This is a halogen attached to the ring, so our electrophile here would be bromine. You can see it's sticking up. Here's the hydrogen sticking down. We have, some electron density here in the ring, but not what we start with benzene, right? Because we have all these positive charges on this ring. So this is our intermediate. Let me take this electrostatic potential map. I'm going to turn it upside down so we can see the bottom. So here's our bromine, here's our hydrogen. Hydrogen is coming out now. Look at this guy. Now, this is a positive species, so there's not a whole lot of electrons messing around, right? But where are the electrons? They're here and here, aren't they? That's a little green splotch. These guys are blue. So these carbons are partially positive. These carbons are partially negative. Now, if we put a substituent here, either ortho or para, and that substituent donated electrons, it would stabilize this intermediate. So the more sophisticated question or answer here is that we're not really directing our substitution by having more electron density ortho and para, but ortho and para in our addition intermediate, if we have electron donating here, that will stabilize a positive charge, make this happier, and so you get more product. What are the fundamentals of physical organic chemistry? What you want to do is to stabilize your intermediate, or the transition state leading to the intermediate. That's the way enzymes catalyze reactions. They stabilize the transition state leading to the intermediate. So, organic chemistry, biochemistry, same thing. This is actually formalized in what's known as the Hammond postulate. This is one of the fundamental things in physical organic chemistry. This is actually his hand-drawn picture from 1955 in his original paper. Basically, what the Hammond postulate says is that the position of the transition state in the reaction coordinate depends on the stability of the intermediate. If your intermediate is very stable, you'll have an early transition state. If the intermediate is very unstable, you have a late transition state. So it moves back and forth. Here we are going to stabilize our intermediate. If we stabilize the intermediate, it also stabilizes the transition state, and therefore you get more products. It's the same fundamental principle for enzyme catalysis. All right. So let's look at a real example then. If we take toluene. Toluene, if you remember our little chart, the methyl group, alkyl groups, are up towards the top. That means that they are activating. Based on our discussion here, if they're activating, they should be releasing electrons in, and they should stabilize the intermediate, leading to ortho and para substitution. So we can do the experiment here. Nitric sulfuric acid, toluene, we get 63% ortho, 34% para. Remember, we get twice as much of this because there are two ortho positions. So for toluene, number one, you get a mixture of products, ortho and para. But the regiochemistry is just what you'd expect. We wind up with ortho and para substitution. On an exam, if I gave you this, I would just write the para, okay? Because it's easier to write. If you write the ortho, it's a little crowded. But remember that you get both products. Yeah?
So the para would be the most stable, right?
No, the para, the electron density that we saw in the previous slide
Yeah.
was ortho and para to where the electrophile adds. So this is ortho
Yeah.
and this is para. So we expect these to be not just activating, but they're also ortho-para directed. We do get a tiny bit of meta, but it's only about 3%. So let's go back to our grand chart here. These guys up top, we said, are activating towards substitution. Starting here with benzene going up, and we include the halogens. As I said before, the halogens are still activating, even though they're more electronegative and they withdraw electrons inductively. They also donate electrons by resonance, just like anisole. Not only are they activating, But these guys are going to be ortho and para directed. So if we do a substitution here on methoxybenzene, we expect ortho and para products. Any questions? All right, the one thing that sticks out as being, like ugly, once again, is why in the world is a methyl group activating? It's magic. Magic is called hyperconjugation. Basically, it's rationalized this way. If we take carbocations like this, we can look at the electrostatic potential maps. We know that a primary is going to be less stable than a tertiary. Now the reason for this, this is less stable because you have big blue splotch here, little blue splotch there. The reason that this happens is this phenomena of hyperconjugation. It's also called, uncomfortably, bond-no bond resonance. The way to do it is to say, okay, here's our primary carbocation. We can take electrons from one of these CH bonds and simply move them in to make a double bond. And this leaves this poor proton sitting out here in space with a positive charge. Now, why can we do that? Because remember, resonance forms aren't real. They're not real. They're limits. You never get to a limit, do you? So, what this tells us is that in hyperconjugation like this, what we have is a resonance intermediate where we have partial positive on the hydrogens, and we reduce the positive charge here. So that is why alkyl groups are activating and ortho-para-directing. Any questions? Go ahead and do this. Predict the product of the substitution. Here we're doing nitration on benzonitrile. Now if you go back and look at your little scheme, the nitrile group is at the bottom, isn't it? So it's deactivating. Step one, you're going to say, all right, well, this is deactivated ring. So it's going to be a slow reaction. The orientation, however, the regiochemistry, in this reaction, only 17% is ortho, 2% is para, 80% is meta. So when you have a deactivating substituent, our orientation isn't ortho or para, it directs meta to itself. Now what we're going to do is rationalize that again. When you're dealing with an electron withdrawing group, remember that this is a lousy reaction. The conclusion we're going to come to is that we go meta because going ortho or para would be a worst case. But let's prove that to ourselves. And we're going to prove it using our resonance forms. As practice, take and draw a resonance form for the electrophile adding meta to our nitrile group. Just go ahead and draw one for me. What you're going to do is take the electron pair from the ring, move it out, and make our bond. We're going to be left with a positive charge here. Now we can delocalize this by resonance, can't we? We can take this electron pair, move it in, and put our positive charge here. And finally, we can do that a third time. Move the electron pair up, put our positive charge here. So we're left with these three resonance forms. What does our hybrid look like? It will have partial positive character here, here, and here. Okay, so this was addition meta to our nitrile. Everyone happy with that? Practice drawing these things. Okay, you'll probably have to do it on the exam. Make sure you can draw a set of resonance forms for the addition. Let's do the same thing now, except let's add the electrophile para. So what I'm going to do is simply take this same electron pair, except I'm going to put my electrophile here. I swing the electron pair out, and here is my para addition. Now, just like before, we can take electrons, move them in. When we do that, we wind up with this resonance form. Again, we can move these electrons up and get this resonance form. So our prediction here is that we would have a resonance hybrid that would look like this. We have positive charge here, here, and here. All right, now number one, we know this is going to be a lousy reaction to begin with. Okay, let's make sure we all know that. Lousy reaction, because the nitrile is sucking electrons up toward the center. But what we want to ask is, which of these two is worse? Which of these two resonance hybrids is worse? Adding beta or adding para? The thing to remember here is that the nitrile is sucking electrons away, isn't it? In this guy, we put a positive charge right here. This carbon's already positive because of the nitrile sucking the electrons up. Therefore, this is a very unstable center now. That means that this, even though it's lousy, is better than this guy. If you put a positive charge next to the group that's pulling off the electrons, that's doubly unstable. Therefore, this is the one, and in fact, we get 81% of this product for bromination and only 2% para. They're both lousy, but this guy is worse. Everyone see that? So finally, let's complete our little table. These guys up top here, from the halogens up, we said are activating and they're ortho-para-directing. These guys from the halogens down are going to be deactivating, and they will be meta-directing. Any questions? So let's look at some very simple problems then. If I take toluene and I do chlorine, iron 3 chloride, first thing you want to do is to go back, think about this. Alkyl group is activating, ortho-para-directing. Right? That's what you say to yourself. Activating, ortho-para-directing. Therefore, what do you put for your answer? We're going to attach our chlorine either ortho or para to the methyl group. On an exam, this would be a perfect answer. You probably didn't even have to include the words orthoisomer. Just give either ortho or para.
Wouldn't that be para?
Yeah, this is para, plus we also get ortho. Ortho is here,
Oh,
remember?
so that's how you wrote that, just so you don't have to draw the other structure?
Right.
Okay.
All right, benzene sulfonic acid, is that activating or deactivating? Look at your chart. It's on the bottom, isn't it? Therefore, this is a deactivated ring. Because it's deactivated, we are going to get meta substitution. Our meta substitution is here at carbon 3 relative to the sulfonic acid. So the product we get is simply that. The nitro group. Nitro group is way down towards the bottom, isn't it? Very deactivated. Really sucks the electrons out like mad. Iodine with copper 2 chloride. That will put an iodine on the ring. Because nitrobenzene is deactivating, this will be meta substitution. Iodine will go to one of the meta positions, and it will look like that. We've already done these two. Take a look at the last one here. What is your reaction? Well, here we're doing a FRIEDEL-CRAFTS acylation, aren't we? We have an acyl halide, Now we know that the FRIEDEL-CRAFTS reaction won't work if you have electron withdrawing groups on the ring. Fortunately, the isopropyl group here is electron donating, isn't it? So it's activating. Because it's activating, we will direct substitution, ortho or para. Go ahead and draw the para isomer for this reaction. Make sure you can draw the product. All simple alkyl groups are going to be ortho-para directing. Our carbonyl is therefore going to be bonded to the para position, and that should be the product. All right, let's do one more exercise here. This one actually isn't going to show up on the exam. That doesn't mean you can fall asleep. But what if, instead of just one substituent on the ring, you had two, and you tried to do electrophilic substitution? For instance, if we had a methoxy group and a methyl group, and we did a bromination, where would the bromine go?
Would it replace the CH3?
Hmm?
Would it replace one of the substituents?
Well, remember, this is going to activate ortho and para, right? So these and this guy. But there's already a methoxy group here. The methoxy group activates ortho and para, but there's a methyl in the para position. So what we're going to do is simply force our substituent, our new bromine here, is either going to go to one of these four carbons. The rule here is so delightfully intuitive. If you go back and look at your chart, who's on top? Who is more activating? The methoxy group. It's above methyl, isn't it? The most powerful group dominates. Therefore, when we do this substitution, it goes ortho to the methoxy group. That's the predominant product. So fortunately, this makes absolute common sense. Let's do it one more time. Again, we have 3-chlorotoluene. We're doing a second chlorination here. Where is it going to go? Think about your methyl group. Where is the methyl group going to send it? It's going to send it ortho to itself or para, right? Where's the chlorine going to send it? Ortho to itself or the para. Therefore, the methyl is going to activate this position, this one, and this one. Chlorine will activate this one, or this one. Bottom line, one of these positions is going to wind up with our new chlorine. Which one? Well, this and this are the predominant isomers that you get. This we actually don't see. Why? Because trying to squeeze the chlorine here in between these two It just doesn't fit very well. Remember, these are big atoms. Again, this makes perfect sense and is easily predictable. Now, we're not going to have an example like this on the exam because it just makes too much sense, too easy. But just make sure you understand it's just a contest of who is the most powerful, if it's a choice. In this case, we didn't get this one because it's just too crowded. All right, there's one more phenomena for substitution reactions that is a little odd. If you take something like fluoro dinitrobenzene and you dump it into strong base, so talking sodium hydroxide or something like that, what you get here is a substitution reaction. The fluorine goes off, the hydroxide goes on where it was. Now, this ring is very electron deficient, isn't it? We have two nitro groups. Very electron deficient. We've dealt with substitution reactions before, haven't we? Way back in chapter, I don't know, 6 or something. What we said was we have two basic substitution mechanisms, SN1 and SN2. If this was an SN2 reaction, remember, in an SN2 reaction, the nucleophile has to attack backside to the leaving group. Remember that? Here it can't, can it? Because it's in the middle of this ring. Therefore, this cannot be an SN2 reaction. Well, the other one we know about is SN1. In SN1, the leaving group leaves, and you get a carbocation. This is one of the worst carbocations you could ever imagine. Not only is it aryl, which is bad, but it's aryl with two nitro groups attached. This is a terrible carbocation. This isn't going to work. What we have here is a new mechanism for substitution. It's called addition-elimination. When we get to chapters 19, 20, whatever, we will see that addition-elimination is a very, very common mechanism when you're dealing with especially carbonyl compounds. In fact, the lab we're going to do on Wednesday is going to involve an addition-elimination reaction. What do we mean by that? It's a two-step reaction. Step one, we're going to take our hydroxide group. It's going to look at this ring. Now, this guy is not an electrophile anymore, is it? It's a nucleophile. It has electrons, and it's looking for something hot, for something positive. Well, this ring is very electron deficient, but the most positive point is going to be here, where the fluorine is attached. So step one, this is just going to go in and add. If it added here, we have to get rid of this electron pair. So let's take and just move it to the next carbon. So what we have done is an addition. We have added the nucleophile to the ring. The Instead of electrophilic aromatic substitution, this is called nucleophilic aromatic substitution, because our nucleophile adds to the ring. Now, why in the world is this okay? Think about what a nitro group really looks like. What does a nitro really look like? We have a nitrogen, and we have these two oxygens. Nitrogen has a positive charge. That's why it's electron withdrawing. One negative charge up here. Well, if we have a pair of electrons here, we can stabilize those by moving them in, putting these guys out on the oxygen, and drawing this. Therefore, this is a stable carbanion because we really move the electrons out onto the oxygen. If you want to play games, you can also take this electron pair, move it here, and put it on this oxygen. So we can do it on both of them. All right, let's go back. The elimination step. We have this carbanion or carbanion character. We've added our nucleophile here. All we're going to do is put the electrons back in our double bond. Either hydroxide or fluorine has to leave if we do that. If hydroxide leaves, we're back where we started. But if fluorine leaves, we wind up with the hydroxybenzene. So we have two steps: addition of the nucleophile, elimination, loss of our leaving group. Now, in order for this to work, the ring has to be really electron deficient. So nucleophilic aromatic substitution, you're talking about something with lots of nitro groups and usually a halogen or a leaving group. Bottom line, aside from the mechanism, the bottom line to remember, leaving group leaves, nucleophile replaces it. Any questions? All right, let's do one more quick section here. Once we add a substituent to the ring, turns out that there are things we can do to it. We're going to, in this very brief thing, we're just going to talk about reduction. So let's say that we did a reaction and we made styrene. Back when we did the introduction to benzene, we said that you could reduce benzene itself to cyclohexane, but that it was a really long, slow reaction. It took a long time. If you can reduce this to cyclohexane, but it takes a long time, that means that if you had something like a double bond out here, and you keep your time and your temperature short, you can reduce this thing it's attached without bothering your ring. So that's good. If we have something with a group that can be reduced, we can do it without messing with our ring. To show you the difference here, this reduces in less than an hour. This takes 200 psi, and it takes basically a day for this thing to go. So this is a very, very slow reaction. Here we reduce the double bond quickly, and then very slowly reduce the ring. Now, there are times when you want this thing to go quickly. Turns out that there are catalysts that have been developed that are better than platinum or palladium. Rhodium is one of them. 25 degrees, 1 atmosphere, again about an hour. You can reduce them both. The nice thing about this is the selectivity. You can do it without touching the ring. There are two other groups that we can reduce easily. In chapter 25, we will meet diazonium salts. Diazonium salts are important because they open up lots and lots of substitution pathways. To make a diazonium salt, you need aniline. Well, you can't introduce this as an electrophilic addition, can you? That wasn't on our list. But nitration is easy. So easy that we even did it. If you take a nitrated benzene, once again, we could use hydrogen, about an hour, room temperature, reduce this smoothly to the amino group. We could also do it using tin, 2-chloride, and acid. Very nice, very smooth reaction, actually, to give aniline. This is one of my favorites. The other thing we can reduce easily is carbonyls that are right next to the ring. We can reduce these either with hydrogen or using this guy, zinc-mercury amalgam. Now, this is the dissolving metal reduction. We've seen dissolving metal reductions. We know that they exist. What you basically do is convert the carbonyl to a CH2. This has an interesting, the Clemmensen reduction has an interesting history. One of Clemmensen's students was trying to do a dissolving metal reduction of an aryl carbonyl. So we had zinc and acid, just like we do with other dissolving metal. And it was in there and it was fizzing, but nothing was happening. It wasn't happening. He was using a thermometer to stir the thing. And, being very frustrated because nothing was happening. And perhaps he stirred a little bit too hard and broke the thermometer. The little wad of mercury fell down with the zinc, formed an amalgam. That's one metal dissolved in another. And the zinc-mercury amalgam instantly catalyzed the reduction. So it's one of these lab accidents that really worked nicely. At least for Clemmensen, his name is still on it. Now, why is this such a neat reaction? Remember, we were trying to make propylbenzene, right? We said we could not do it using propyl chloride and aluminum chloride because instead of this guy, the carbocation would rearrange and we would get the isopropyl as our product. So it didn't work, right? But remember, FRIEDEL-CRAFTS acylation is not prone to rearrangement, is it? Therefore, instead of using this, if we simply used propanyl chloride, standard FRIEDEL-CRAFTS, we would make this aryl ketone, wouldn't we? Once we make the aryl ketone, how do we get propylbenzene? We do the Clemmensen reduction. So, Clemmensen reduction of aryl ketones is the standard way to introduce a group that is prone to rearrangement into a benzene ring. Introduce it as the acyl group here, and then simply reduce it off. I can almost promise you that on your exam, you will be asked to do a synthesis somewhat like this. You do the FRIEDEL-CRAFTS acylation and then the reduction. All right, speaking of exams, let's do, on your exam you will have synthesis. This is an example of a synthesis problem. Let's just close up today with a really cute basic synthesis. I will hush for a moment, but I'd like you to start with benzene and make 4-bromobenzoic acid. Now remember, when you do a synthesis, you have to work backwards. You have to think backwards. You start with your product and say, what is it? How many ways do I know to make it? Then you pick a reaction and you do it. So what is this? It's a benzoic acid, right? In all the electrophilic things that we've looked at today, did we ever add a carboxylic acid? No. No. But if you go back to chapter 15, we had a very nice reaction that gave us aryl benzoic acid, didn't we? Oxidation of an alkyl group. The only way we know to make an aryl carboxylic acid is by taking an alkyl group, something like a methyl, and oxidizing it, either with manganate or, like we did in lab, chromate. So what you do now for your synthesis is say, okay, this used to be a methyl group. So working backwards, we're going to write an intermediate here, where this is a methyl group, and our reaction conditions are the oxidation. Think about what you would write. Our carboxylate used to be a methyl group, could have been an ethyl, but methyl's easier. Our oxidation, just something like permanganate and acid or water. Permanganate and water even works. So if we had 4-bromotoluene, and we oxidize with permanganate, we would get 4-bromobenzoic acid. Now remember, we're starting with benzene. So we're going to have to make, next, 4-bromotoluene. How are we going to do that? Well, we could actually do this two ways, couldn't we? The methyl group is para-directing, right? So we could take toluene and stick on a bromine. So our previous reaction then starts with toluene, and we simply do bromination. Go ahead and write it.
So we have bromination of toluene.
That's it.
Yeah, it's pretty simple.
How simple. And it goes to the para position. Start off with toluene, do bromine, iron 3 bromide.
No, it's not built up.
and you get 4-bromotoluene. Now remember, we're starting with benzene, so how do you make toluene? FRIEDEL-CRAFTS reaction, right? So all we have to do is take benzene, alkylate it, something like chloromethane with aluminum chloride. So pathway number 1 here, we methylate, we brominate, and then we oxidize. Now, we can do this by pathway number 2 also, can't we? In pathway number 2, we would start off with bromobenzene, methylate, we make bromobenzene from benzene by bromination. Go ahead and write the pathway. Start with benzene, make bromobenzene, add a methyl group. For the methylation of bromobenzene, bromine is going to direct para. All we need is bromobenzene and something like chloromethane, aluminum chloride. How do we make bromobenzene? Bromination of benzene. And the full path would look like this. Now this is actually a 3-step synthesis. We're not going to do 3s yet. On your exam, you'll be asked to do 2s, but not 3s. So 1s and 2s on the exam, but not 3s yet. But isn't it nice and simple and logical? You start here, say, how do I know to make a carboxylic acid? Only by oxidation. So I need this. How can I make that? Toluene and bromination. Or bromobenzene and methylation. And how do I make these guys? Methylation or bromination of benzene. Synthesis is just so much fun. All right, thus endeth chapter 16. Remember, on Wednesday we will do, I think the lab is on page 273. It's formation of benzophenone oxime. Very simple little reaction. Oxime is a carbon-nitrogen double bond with an OH attached to the nitrogen. Nice and simple, very standard prep reaction. It is an example of an addition-elimination reaction. And I'll show you that for next week.
So quiz is on Monday?
The quiz will be a week from today. And the sample exam will go online. Hope to have it done soon. So it'll be available on Wednesday, I hope.
And the exam will be a week from next Monday.
Right. Exam is a week from next month.
No, it's all right.
That's cool. I'm not telling
Do a specific time on Monday?
you. No, we just need some ultimate understanding that.
Did you guys go through this?
We're done, I'm guessing?
We're done.
Quick question. So,
I
I don't know if I remember this because I was going to ask you this like 2 minutes ago. This second to last reaction, this one, yeah. Could you have just done it using that, or using?
Remember, we tried it with this guy.
That's what I was going to say.
It's not going to work.
Okay.
Because it rearranges to the isopropyl double cation.
Oh, and because
Won't
that.
work.
Okay.
But this guy,
Because that rearranges. All right. Gotcha.
this one